I'm going to talk this morning about what is code quality. As was mentioned, I have actually been on the program committee all 3 years of the conference. I've enjoyed that very much. I agree that the quality of the papers is increasing every year, and that the people submitting these papers are definitely highly skilled in their background, in their dedication to the issue and the notion of what is code quality. I'm going to talk about how some of these characteristics, or what we have considered to be quality code over the years, began back in 1968, which is when I had my first programming job. I worked in a bank. I wrote COBOL programs for the bank, and I wrote assembler programs for extending the capabilities of the computer, which was still somewhat of a novelty. We actually had our own Burroughs computer engineer, electrical engineer, sitting on site most of the time, because the computer would occasionally have these little electromechanical glitches and have to be fixed by a technician. So code quality has grown significantly over the years. The way that people would talk about code quality was to discuss a various set of qualities or characteristics of the software, of the code. A lot of these in English ended in the letters ITY or ILITY. And so they came to be called the ilities collectively, the ilities of code. And that's where we're going to start. And then we're going to try and take you in a perhaps somewhat uncomfortable direction towards the very end. Uncomfortable only because all of you are really, really good software engineers. You have your technical chops down very, very well. And so I'm going to take you outside of that comfort zone a little bit, I hope, towards the end of this presentation. So we're going to start about with the ilities, and we're going to go to a mystical and maybe an ethical dimension to doing this kind of thing. So in 1968, there were three ilities. There were three qualities that code had to have. Legibility. You had to be able to differentiate the numeral 7 from the capital letter Z. So one of the characteristics of your code, you had to put the little crossbar on your capital Z in the German style so that it could be differentiated from a 7. The illustration on the left that is a little bit hard to see, that's a COBOL coding sheet. So in 1968, you wrote your code on paper. You had these big tablets or pads of this, they were green usually, of this 80-column format plus a 5-column sequencing number. And that's where you wrote your code. And that's where legibility comes in, is that you had to write your program on a piece of paper. That piece of paper was then taken to a key punch operator who typed that code onto Hollerith cards. You probably, a lot of you, some of you have some gray hair, but a lot of you have probably never seen a Hollerith card that was the way that you input data and you input your programs actually into the computer. It's a hard paperboard card, and it has holes punched out in it. And so the machine that was used was a key punch machine. And you had these operators, most of them were women, that basically functioned as a kind of a typist. They would read these sheets, so they had to be legible. They're doing this very fast, and they would type your program onto a set of cards, and then that would be input into the computer. Usually you would input your program in the afternoon when you had some time, or when the machine had some time to work with your with coding and things of this sort, instead of operational business, and you would get a printout of your program. The program would run. You might get a report, an error report of some sort or another. If you really messed up, you would get what was called a core dump, which is about 500 pages of paper depicting the status, the hexadecimal status of the core memory of the computer. And that's how you went about debugging your program. Reading 500 pages of dense hexadecimal code is not an easy way to debug a program. So some of your qualities, some of the characteristics of your program were rather severe. The sequencing number on the program, as I said, you translate this program into a set of Hollerith cards. They usually were blank. You had no way of telling what was actually on the card. The year after I started, they started printing on top of the card, so you could actually see what the card code was. But you can imagine you're carrying a big deck of cards, 900 cards, and it is fairly bulky. And you're walking down the hall and the rubber band that is holding those cards together breaks and you trip, and your cards are now spread all across the floor in some kind of a random order. Well, now your program is a set of random instructions. It's not a very good program. And if you don't have sequence numbers on your card, there's no way in the world you're going to assemble that deck of Hollerith cards back into a program that can be read by the machine. So these qualities were very, very, very important in 1968. Today, nobody would think twice about any of these kinds of things. By the 1970s, we started adding a whole bunch of additional ilities. One of the big focuses in 1970 and the early part of the 1980s was this notion of provability. You had to be able to prove that your program was correct in some kind of mathematical or logical fashion. The amount of time and effort that was invested in trying to prove that your program was correct was immense. And of course, it was useless for the most part, because nobody was able to prove that a program over 10, 15 lines of code was formally provable. But we added a number of different kinds of things, including efficiency, evolvability, degradability. Degradability was an interesting one in 1968. If your program ran, it was not unlikely that you would get some kind of an error. Perhaps one of the lines of code was misread by the computer when the Hollerith card was entered into the machine. And you didn't want your program to fail at that point. You wanted it to go into a suspended state, a degraded state, and you had a binder full of instructions that you would give to the computer operator, and the computer operator would use a punch panel on the front of the computer to enter in hexadecimal code, sometimes binary code, but usually hexadecimal code, to step the computer one step at a time through a set of instructions in order to hit a point where it could be corrected and your program could resume running. So the idea of having a program that went into this degraded operational status instead of just failing outright was critical. Again, the turnaround time on a lot of these things was 24 hours, 48 hours. And so you didn't want your program failing, because that's 2 days work that you're going to have to redo. By the 80s and 90s and today, if you go into Wikipedia and ask what are all the ilities that are available, you get this list of 86 qualities that your software is expected to have. Now, I'm sure that everybody that is at this conference could look at their programs and say, oh yeah, my program, my code satisfies all of these requirements simultaneously. Those of us that are more mortal have some difficulty. Plus, a lot of these things, like the provability, are no longer overwhelmingly critical or considered to be overwhelmingly critical, or characteristics um, of your code. A lot of them are really, really interesting in terms of the context that they came up with. Survivability was an interesting thing. It had a great deal to do with uh, uh, electrical engineering, that you had to write a program that would compile and would run in such a fashion that it could survive a nearby EMP pulse from a nuclear bomb. In the 70s especially, there was a lot of interest in whether or not our programs, our software, our code that we were writing could actually survive something like a nuclear attack. Um, Nobody worries about that much anymore, at least not as far as our software goes. We might worry about our skins, but we don't worry that much about our software having these kinds of abilities. But it's an interesting exercise to go through Wikipedia and look at some of these kinds of things and just ask, what did it mean? Why was it considered to be an essential aspect of code quality at this point in time? Instead of looking at all 86 at once, it's useful to put them into different kinds of groups that are easier to understand or to look at in context. The group of qualities that most of you are really familiar with would be the ones that are considered to be intrinsic to the code, the kind of quality issues, the kind of problems that can be exposed with some form of static analysis. Most of the contributions to this conference are in that kind of category. Some examples of how you go about analyzing the quality of your code includes obvious things like the cyclomatic complexity, the ACID test for database related code, and then the old standbys, modularity, coupling, and cohesion. It's really amazing in universities today, in computer science or software engineering programs. The notion of modularity and cohesion is talked about in that kinds of terms. But if you ask your students, or if you ask people at conferences like this to identify what are the different types of coupling, what are the different types of cohesion, and which of them are good, which of them are worse, very few people actually can give you solid answers. But this is the foundation for a lot of the static analysis and a lot of concerns with code quality that have shown up over the years. So this is one group. It's a group that people at this conference would be more familiar with, these kinds of ilities. In today's world, the nature, the manner in which software is developed has changed significantly. In 1968, I wrote programs as a solo programmer. I almost never had anybody collaborate with me on a program, other than the fact of walking over to another cubicle and saying, I have been staring at this thing all day long. I cannot see where the error is. And the person in the cubicle could say, oh, it's right here on line 17. You misspelled this word. That should be an E, not a 3. Something of this sort. And this has to do with the psychology of the mind and not being able to see your own errors. But that was the extent of collaboration. Today's software, of course, is maintained by teams or teams of teams. And so good quality code is one that satisfies a lot of what we might call social characteristics or social qualities of the code. Is your code readable? Can other people on the team read your code and understand what it's supposed to do? Are you using appropriate use of metaphor when you name your variables? This became a huge deal in the 80s and early 90s when people were doing object-oriented programming. The use of metaphor, and this is not a technical thing. This is poetry, but the naming variables, naming your functions, If you did that correctly, you were making metaphors and relevance to the real world. Can your programs be refactored? Is all of your code, all of your production code, has it been looked at and reviewed and developed with 4 eyes, pair programming? The aspects of what was considered quality code switched to these communicational and these kinds of social characteristics of your code, and far less on the technical correctness of your code, because you have to develop this in groups of people. And so a lot of the previous comments about styles and modes of programming show up in this kind of a context. Different communities have different kinds of idioms that they use when they're writing code. They have different kinds of style. Different companies set, unfortunately, different kinds of standards for what is considered to be appropriate or good or quality code at our company or at our university. And these kinds of things creep in, and it can be confusing if you go from one company to another company, or if you change languages and you go from COBOL or C or something of this sort and try and learn Smalltalk. A biggest part of that conversion was learning what the idiom and the style appropriate to the Smalltalk programming language, which is very different than it was for C or C++ or these other kinds of languages. And then the reverse is true. I can't tell you how many people were just seriously disappointed when they had to move from Smalltalk to Java, because Java was such a horrible language in terms of the idiom and style of people that had been grown up or had become experts in Smalltalk. In a lot of ways, you can take the entire agile software development movement and say that that was a reaction to a whole bunch of people who are really skilled in the world of Smalltalk having to move to Java and invent an entire new kinds of idiom and style. Ask Kent Beck sometime whether he likes Java or Smalltalk better than which language he prefers. And these days you'll get, well, Java's okay, because that's what he gets paid to do. But have a beer with Kent Beck and ask him that question, and you'll get a long lecture about Smalltalk being so much better in terms of idiom and style and expressibility. Also in the 80s and 90s, we started to move a little bit away from the more technical kinds of aspects of code. We started worrying about quality code had to have beauty. It had to have elegance. The 80s in particular, we saw a lot of people writing columns in popular press and programming press. John Bentley, for instance, had a column called Programming Pearls, and these were converted into a series of books with the same title. And these are code or segments of code or small short programs that supposedly were beautiful in some kind of way, that these were really elegant expressions of how you would code or how you would solve a problem in a particular programming language. There's another book by Andy Oram and Greg Wilson called Beautiful Code. The same kind of notion. Your quality code had to be more than technical quality. It had to have this aesthetic quality to it. And part of that too comes out of the social kinds of characteristics of what your code. A lot of it has to do with things like simplicity. What makes code elegant oftentimes is code that is simple. And simple doesn't just mean a few lines of code. It has some other kind of additional kind of a quality to it. There was an architect, Christopher Alexander. He just recently died about a year ago. But he was very concerned with the quality of the built environment architecture. Christopher Alexander had a big influence on the software community with his idea or notion of patterns. So he wrote a book called A Pattern Language. It had 256 patterns, which were design solutions in context for the built environment, for the architectural kind of environment. This inspired the software community via the auspices of Ward Cunningham and Kent Beck, were the first people to bring it to the software community at an OOPSLA conference in Washington, D.C. And it became a huge movement. Most people have heard of the software patterns movement. Many of you have probably contributed papers to the various kinds of programming languages and the PLOP conferences. I forget what the acronym is now. But these ideas, and Alexander was very concerned in his book, The Timeless Way of Building, about QWAN, the quality without a name. So now you as a programmer, you've got to figure out, gee, is this, does my program not only run and function and is readable and expressible and efficient, it has to have this mystical quality called QWAN. And QWAN is something that's supposed to transcends time. So various people over time can sense and seek QWAN. You can't technically define what it is, but you know that it's there, and it transcends culture. So this is a kind of a really interesting notion of how do you translate this into code. In the patterns community, they called it habitability. And the notion here again is that your code starts to have this kind of QWAN or this kind of mystical essence. If other people come to your code and have to work with your code, they have to debug it, a year or so after you wrote it, or adapt it, or change it to new kinds of circumstances. If they feel comfortable, are they happy doing this? Is this easy for them? Do they feel like when they sit down with your code, it's like sitting down with a good novel, that they really enjoy living in that world, the same way that you might enjoy going into a written fictional novel and being happy with the world that the author has created for you? So this is kind of interesting. It's a real challenge for people that are technically oriented and that are really well-developed coders like all of you. In the future, we have a whole additional set of problems that we're going to have to figure out, and these are going to be reflected in our concept or our understanding of what we mean by quality code. You're going to have some new or some re-emphasized ilities. Reusability is a huge one. We actually, in practice, reuse a lot of code. There are a lot of public libraries. There are a lot of sites out there where you can go and borrow somebody else's code and integrate it into your program. This can be a huge problem because a lot of that is not necessarily written or built or designed to be used in different kinds of contexts. It also creates some really interesting dependencies. There was a bit of code. It was called left pad, and it was written by a software developer and put up on one of these public sites. And it ended up being reused in almost all the software out there that had to do with the internet. And the author of that code got into a dispute with the site where it was hosted and removed it. And all of a sudden, all of this software, all of these big time sites on the internet failed because they didn't have access to that 4 lines of borrowed code from this site. If you do a Google search sometime, look for the man who broke the internet, and you'll find the history of this dispute and how it ended up being resolved. Producibility, can we even write the code? In the 80s, when Ronald Reagan was president of the United States, he started an initiative called the Strategic Defense Initiative, and it was supposed to prevent or deter a nuclear attack on the United States or prevent the success of such an attack. David Parnas was the software engineer chosen to head that program. David Parnas and his team of software developers, who were the best and the brightest in the United States, which is not saying anything compared to the best and the brightest in Russia, but we try. But David Parnas and his team of experts, they came to the conclusion that they could not write this software. It was not producible. It was too large, it was too complex, and the only feasible way, or the only way of testing it, which is not feasible, was that you would have to provoke a nuclear attack and see if it worked, see if it prevented all the missiles from landing on the United States. That's not the kind of software testing I want to do. But these are going to be different kinds of issues. I wrote a short paper. You can find it on medium.com. It's called IT is Not Sustainable. The amount of power consumption consumed by server farms around the world is equal to, these are just the server farms, not the software and companies or your PC laptops or things of that sort, but just the different kinds of server farms, especially big companies like the Amazon cloud. The power consumption of those is equal to the annual power consumption of the British Isles of Great Britain. That's a lot of power. And most of it is produced with greenhouse gases. You know, it's coal, because most power comes from coal, natural gas, things of this sort. And so it's not a really sustainable kind of an idea. We're going to have to start worrying about, you know, is our code going to have a sustainable ecological footprint? And this sounds a little bit weird, but it's very real. Domain congruency. Does our code reflect the reality of the domain? Is it usable? Is it useful? There's a small book. It's the result of a study by Carnegie Mellon University in the United States, and it's called Ultra Large Scale Systems. But they're looking at these kinds of very massive software systems that we're going to have to create in the future. These systems are going to be comprised of heterogeneous components created by different companies, different people. You're going to have conflicts of style. You're going to have conflicts of idiom. But nevertheless, these things are going to be out there in some kind of global network, and they have to get along. They have to work and function efficiently and effectively together, even though they come from heterogeneous sources. The code is going to have to be self-correcting, adapting, and evolving. The code is so complex that it's rapidly becoming beyond human comprehension to understand what it is. You're going to have AIs like ChatGPT right now writing the code. And how are humans going to understand that code, or how are they going to interact with it? And this becomes a real problem. How do you detect malware? How do you detect bad actors? The one that I find really, really interesting in this study is that how are you going to integrate human beings into your software systems as computational components? The analogy or the metaphor would be, how do you call a human being and take advantage of their internal programming as a sub routine or a function in your Java code? How exactly are you going to do that? What is the call structure going to be, and what are you going to get returned when you send something off to a human being? And I'm going to end by going back to the beginning. I said we're going to talk about code quality. I'm going to end with just asking the question, you know, what does it matter? Does it really matter whether your code has any quality or not? If you have a set of known inputs, and they go into a computational black box, and you get the corrected, the expected and the correct outputs from that black box. What exactly does it matter what's inside the box or what characteristics it has? A little side corollary to this is that most computers and most software languages are at some fundamental level Turing machines. Well, Turing's model of computation, which the industry is based on, has one component of a Turing machine. It's that infinite tape of binary ones and zeros that is both your data and your program. And this tape goes through and becomes the way that the machine functions. Well, that tape is infinite, which means that there's an infinite number of possible programs on that tape. If you have an infinite tape, if you have an infinite space for your code, you can write anything you want, and eventually you can come up with something that's going to work, no matter how baroque or elaborate or poor quality it may be. There's going to be an infinite number of incorrect programs, programs that have zero quality. There's going to be an infinite number of correct programs. An obvious example of this is just to look at different programs that are written in different programming languages. You can write a correct program, a hello world program in C, in Smalltalk, in Java, in all these different kinds of languages. It will be at some level fundamentally different, but at another level, they're identical. They're the same. How do you choose between the correctness of one or the other? You can come up with artificial or arbitrary ways of comparing a program and saying one has more quality than another. So for instance, when I was in graduate school, I led a team, and we were a C team, and we were writing code for engineers in the College of Engineering at the University of Wisconsin. And we would, in the C programming language, I can write a hello world program in 2 lines of code, 2 lines of source code. We had the opportunity to work with the very first 0.9 beta release of the Windows Software Development Toolkit. In order to write hello world in Windows at that point in time, you had to write a little over 500 lines of source code. And then the include statement brought in another 50 or 60,000 lines of Microsoft's code. But it worked. You know, hello world showed up there on the screen just like it did in the C program. Well, which one of those 2 programs has the greater quality? For me, the C program did, because I could read it. The Windows program, I had no clue or no concern. And so the last statement I'm going to say is that code quality, we may shift from intrinsic, the quality of what's inside of that black box, and start worrying a lot more about what are those outputs from that black box, and what effect does it have on the world? Is code quality is going to be quality that makes human life better, or that makes living on the planet better, or helps us survive the kinds of technological things that we are doing. So the quality of your code is not what is inside the black box, but the effect of that black box on the rest of the world. Different kind of a challenge, a different set of challenges, but it's one that's available. Okay, I may have gone a little bit long, but I think there's some time for questions. So I'll turn it back over to our moderator.
I have a few questions for you, if you don't mind. My biggest concern, I totally agree about the aesthetics you mentioned and about elegancy of the code. My question is, how can we measure that? And that's the question which I face very often when I try to put these ideas into practice. And then people ask me back, like, how exactly we can measure that, because it's very subjective. One person thinks it's a high quality code, another thinks it's a low quality. So do you think it's possible to measure that somehow?
I do not think that there is an objective measure for how to do that. it ends up coming down to communities and setting, community standards. So yes, I think that you could write, and Kent Beck has written a book on small. You've written some books on object-oriented programming that say, here are some ways of thinking about object-oriented programming that leads to higher quality code. But that's only within a community that has some significant background in a language like Smalltalk. You might get people that come from the COBOL community to agree with you and to agree with a lot of your standards. I don't know how successful you have been getting the Java community to agree with you. But yeah, I mean, it's a challenge, but it's a social engineering challenge. It's not an objective um, uh, at the level of the code statements itself challenge. It's how do you convince a community of people that this is the right way or the best way of doing it? And I think you can establish a community, but that's as far as you go. You're not going to come up with an objective standard that is universal. I'm pessimistic anyway.
It is, yeah, indeed. Because without the numbers, we experience hard time convincing the management that the code quality matters. When we show them the bugs, when we show them the bug reports, and we say we're going to have less bugs, then they're ready to give us the budget for that. They're ready to pay for this work. But if we come to them and say this code will become better, it will be more elegant, it will be more aesthetic, it will give us more pleasure to work with, then they kind of, they're not going to give us the money. That's the concern.
This is true. But let me give you a little bit of a counter example. So this comes from the early days of object-oriented programming, and the two competing languages at that point in time were Smalltalk and C++. Java was just a gleam in sun's eye. It didn't exist. And there was a project, they reported on this project at a conference I sponsored in '96 called Current Object Practice and Experience. But they sat down and they said, we need to write this very technical bit of code. It was for a telephone operating system, switching system. And so the program had a very, very strict time budget measured in milliseconds that this program had to operate. So this company set to work on this program, and they created two teams. One of them was a Smalltalk team. One of them was a C++ team. In 6 months, the Smalltalk team had written the program, tested it, function, it worked. But of course, it didn't meet the time budget because Smalltalk is a very, very, very slow language. So once they had the program up and running, they did some very technical kinds of tweaks, and they precompiled methods and some other kinds of things of this sort, and they met the time budget, and they did all of this in 6 months. The C++ team, a little over a year into the program, still hadn't finished, still hadn't written the correct program. But management said and looked at this and says, yeah, but Smalltalk, the Smalltalk programmers are hard to come by. They cost a lot more money. Nobody really understands this stuff. We're going to go with the C++ code anyway. So, I mean, managers don't necessarily make their decisions on rational choices, and they should. And if you come up with a very simple kind of measure like the number of bugs, yeah, they're going to jump on that because they understand it. They are never going to understand the QWAN or elegance or beauty or things of this sort. It's difficult for us to understand it, but convincing management, you're correct. You're going to have a hard time.
I actually have a hope in this direction because I didn't have it for years, but now I have one. With the appearance of ChatGPT and similar technologies, which will develop, maybe in the future, there will be a possibility to ask this large language model like ChatGPT, what is a subjective opinion about the piece of code? And the ChatGPT will say, I believe this code is elegant enough, or I believe this code is of a low quality. Not objectively, without the numbers, without the number of bugs or lines of code, but just subjectively. But if it's going to be some sort of a large instrument which is trustable by everybody in the world, of all the managers, then maybe managers will start to believe in that, and then we will be able to, as programmers, we will be able to rely on that opinion and say that, look, this system says the code of this quality is low. I cannot explain why, there's no numbers, but it's a feeling coming from a huge smart AI. What do you think about this?
I agree with you in principle that yes, it may be possible for these large language models or other kinds of AI systems, just because of the massive amount of information that they're bringing to bear on the problem. It's not a short-term kind of a solution. Look at the problems that ChatGPT has with racial bias. It's how to do with how these models are being trained. And until we figure out how to do those kinds of, how do we train ChatGPT to recognize QWAN? I mean, we still have to train these things to do what they do. If we can figure that out, then I agree with you. I think that that there is some significant possibilities in that regard, and that it may be something that you can use to convince managers.
Okay, sounds good. And after you mentioned the social aspect of the code quality, I think that maybe we, in our future conferences, which we're going to organize in the future, maybe we need to somehow invite more papers on this subject, where the social aspect is intersected with the technical aspect of code quality.
Most definitely. And there was a fairly significant amount of effort along these lines. If you go back in the mid 80s to the late 80s, when people were, when object oriented was the new thing, the hot thing, and people were looking at these kinds of things. You can look at Kent Beck's Small Talk Practice Patterns book. You can look at your books, which are talking about these standards, idioms, style. These are the social aspects, and trying to build a consensus community around them. And yes, I think it would be a really worthwhile effort to include or incorporate that kind of thing in this conference. Put an anthropologist or two on your program committee to help review these technical papers.
Okay, that's a good summary. Oh, we have a question from the audience, Sergey.
Yeah, maybe a couple of questions as a continuation of the previous question somehow. If you are talking about the role of a human in the code quality evaluation, how we can distinguish the subjective part and objective part of this evaluation, because humans are really subjective, and they rely on the experience and expertise, and that's a personal thing, and it changes from time to time. That's the first thing. And the second question may be, again, as a continuation of the previous one, if we consider the complex adaptive systems, usually in a complex system, we consider a lot of elements. And in this case, would it be interesting to consider the especially social aspect as a part of having a programming language and programs as a medium for interaction, and this is a kind of a multi-subjective quality of a code used also to communicate between people and to build something new collectively. What do you think about this?
Well, I agree. And what you're describing in a lot of ways is the challenge that I confront every day as a professor, trying to teach people how to write code, how to write quality code, and how to work with each other. And you get a lot of resistance, and it's hard. In the American education system, there are a lot of things that mitigate against it. We don't like people working in teams where you cannot identify an individual and say, this person gets an A and this person gets a B. You know, this idea, but when they get out in the real world, they're going to have to function as a team. So there's a whole set of skills that you have to teach people, the so-called soft skills. You know, how do you get along with your team members? How do you communicate with your team members? There are cultural issues that are involved in there. There are psychosexual issues that are involved there. Pair programming. You observe people trying to do pair programming, you know, working together in close proximity. There's some very famous kinds of pictures of mixed gender, male and female pair programmers, and they're sitting sharing this keyboard, but they're sitting, you know, they're leaning away from each other, because the genders in the U.S. have very different kind of social comfort distance, you know, distances where they're socially comfortable working together. And two guys working together, they have no problem rubbing shoulders, but a man and a woman working together, they shy away from that. When I was teaching in India, I saw groups of three. So there would be two guys sitting at in chairs at the keyboard, and there would be a third gentleman behind them with his arms around their shoulders and his head between theirs, doing triple programming. You know, that's a cultural thing that you would never ever see in the United States, especially with three guys. But you know, how do you deal with, how do you incorporate them? How do you put them into a class where you've got to teach C programming as C programming, you know, so that each person knows how to do the language? It's a challenge, but it's one that we have to figure out.
Yeah, it's really interesting because it's a combination of psychological, sociological skills and hard skills being mixed in the one medium to interact.
Yeah, and something, you know, that goes towards that is conferences, you know, like this one. Now, the true success of this conference is going to be when you have papers submitted from 117 countries.
And we need an anthropologist for the next year. That's for sure, in the program committee.
Well, you actually had one the last 3 years, because that's what my PhD is, in cultural anthropology or cognitive anthropology. But yes, you need another one.